Okay, so will we get started? Are there any questions before we get started? So what I am planning to do today is to more or less continue where we left off last time. I was hoping last time that they would be done with, so I was going to do this idea of explaining why a bunch of traditional areas, information retrieval, information integration, and data mining, and social networks are going to be basically we're going to start using them and then expand them to the case of web. So this is basically what that is the picture that we show, right? And so I was going to do this, and I think I was hoping to do all of them, but we did the information retrieval part last time. So there are things that information retrieval does. We'll come back to the details of it very soon. And then there are things that web adds that makes it easier some ways and harder in some other ways, and then we have to handle those challenges. That's what information retrieval. So I'm continuing that stream for the other three topics. So last time I showed you at the beginning of the class, I said that this particular piece probably won't make too much sense now. Will make more sense after the class is over. And I used a quote from Kierkegaard, if you remember. And now I'm using a quote from somebody else, which also says pretty much the same thing. That you can't connect the dots looking forward, you can only connect them looking backwards. So you have to trust that the dots will somehow connect in your future. So in this case, you have to trust me. Can anybody tell me who said this? Steve Jobs. Steve Jobs. Okay, so obviously we are all thinking of Steve Jobs because let's hope that the guy gets better. So this was part of his Stanford commencement address. Okay, but again, the point is in this case, apart from good wishes to him, the point for us is that this particular discussion makes a lot more sense after the course is over. But on the other hand, you need to have a map as to where you're going. Okay, social networks. Traditional model of social network basically, as I said, social networks existed, okay, before Facebook and Friendsters and so on. So the traditional model of a social network is that you're given a set of entities and their relations. You are supposed to return useful information about that network, such as the measures of centrality, notions of importance of the entities in the network, propagation of trust, and then finding paths through the networks to see how you can reach somebody in the network. And then these can be used for a variety of things, including analyzing the spread of diseases, spread of rumors, popularity of people, importance of papers in scientific disciplines, which paper is the most important one based on who is citing them and so on. That's the kind of thing that was done in social networks. And we use social networks analysis on the web, both in the obvious ways, such as things like Facebook that you know of, and also in somewhat non-obvious ways. Pages talk to each other, they point to each other. So pages are a network, a social network. You created pages and they're pointing to each other. So there's a social network of pages, and you can use some of the same ideas to analyze the pages. In some sense, one can think of ideas such as PageRank essentially as application of social network ideas to the web pages. Okay, and so the big difference is that some of the differences are that you have a big scale here, you have many more entities than the normal social networks that people used to write on the back of piece of paper. You have something that's easier, something that was harder here, maybe partly easier here, is sometimes you have explicit links, pages might be pointing to each other, or you might put a friend link on your Facebook page or something. So there are explicit ways of following links. These are some of the differences. But then some of these, actually the fact that there are explicit links makes things easier in some sense in terms of analyzing social networks. And one big thing that makes social networks easier on the web is most of the social networks that you analyze on the web, somebody has centralized access to the entire network. Okay, so Facebook knows, I mean, to the extent you made the mistake of having a Facebook account, which I don't, Facebook knows who your friends are and who their friends are and what do they like and what you like, and every once in a while they'll say, it's all private, we are not going to misuse this. Okay, but so Facebook knows. Okay, and so Facebook can actually compute the social distance between any two random people among these 500 million people. In normal social networks, the hardest part is computing that network, because I don't know. I know that, I know some of you now. I've seen it like 3 days in a row, and then I don't know who you know. Okay, the nice thing to be able to say is that, to talk to a third person and say, oh, by the way, we share this link. This guy is in my class and you seem to be this guy's friend, so we have this link. But I don't know who your friends are. I have no actual access to it. And so most of the interesting part in the traversal of social networks in the human societies is being able to traverse it. So among which of my friends, so I suddenly need like a good plumber. Okay, which of my friends might know a good plumber? I suddenly need information about some sociological research. Which of my friends should I ask for? Which of my friends might know somebody who might know a good sociologist? I mean, I can always say, put all my friends in an emailing list and say, anytime I need something, send email to all of them, just like I send email to the class list, saying, guys, stop doing what you're doing and tell me, how I can find a sociologist. And then they will send their mail to their friends and broadcast, and obviously the world will take care of me. Okay, but that will work maybe once, right? But it's not going to work normally. And so the issue is, in normal social networks, you have to figure out which neighbor to follow. For Facebook, it knows the entire network, so it can almost tell you who you should ask. Of course, they don't necessarily for you, because of the view that you get on the network is constrained. But somebody knows the entire network. Whereas for the human societies, unless you believe there is an all-knowing God kind of hovering around us and looking around what we are doing, there is nobody who knows the entire social network. Okay, so because of which some problems are pretty hard to solve in normal social networks become extremely easy to solve in these large-scale social networks, because you have the network in front of you. Okay. So anyway, consequently, what you want to do on the web in the social networks is you may want to consider ranking results that somehow takes into account the structure of the network. Okay. For example, you might like of the various books that might satisfy the answer to your keyword query, various documents that might satisfy the answer to your keyword query. You might like a certain specific ones that your friends also like. So I might want to tell you that. Okay, maybe and also if you're just ranking the pages, web pages. Right? Basically, if you assume that the web pages themselves make a network through their link structure, then you can use some of the same social network ideas to talk about ideas like authorities and hubs and page rank, which are ways of talking about which page is the most important page. Very similar to which person in a network is the most important person. And it turns out, for example, there are multiple ways of deciding the importance of entities in a network, and some of them make sense for this. Okay, the other thing that social networks actually help, and sometimes is actually recommendations. And one of the interesting things here is that you may not even know. So here's the interesting thing. Suppose I have the social network of my friends, And some of my friends bought, a CD of music. Nobody buys music. They just stole music from somewhere. Now the question is, should I also steal music from the same place or not? That same piece of music, right? Do I necessarily share my musical interests with my friends' musical interests? No. Just because if you have access to my social network, just because one day you suddenly find that Rao's friends are X, Y, and Z, and they all like this piece of music, you can't necessarily assume that I like that. Maybe I hang around with them not because of their musical content, musical taste, but despite their musical taste. I have other things that I like. That's why I hang around with them. Do you see what I'm saying? So the question then is, when you're when you're using the social network structure, to recommend, sometimes what matters is not the explicit links, but the implicit things. Okay? In particular, I want to make the distinction between friends versus soulmates. Okay? Friends are the ones that you put links to in the social network. And you know they exist already. When somebody says, I found my soulmate, they never say, I was just looking at my immediate friend circle and I decided A is my soulmate. It never happens that way. Right? The reason they found soulmate is they didn't even know this soulmate existed. And suddenly they happen to have the same interests in a certain bunch of things, and so, oh my God, I really like to hang around with this person. Maybe I'll friend them now. Okay? Right? Who do you think finds your soulmates in a very crass commercial sense every day for you? eHarmony. Well, you need to have, I said crass commercials, but maybe you're right. Who else? Yeah, I understand. That's, get out of that mode. Think of other, I'm asking you to bend your thinking a bit. Okay? If you ever go on to Amazon and you started, kind of looking at a particular book and a particular CD, then they'll say, maybe you'll also like this other one. How did they figure this out?
By using the wisdom of crowd.
What?
By using the wisdom of crowd, the other persons were...
It's not necessarily wisdom of crowds. If it's wisdom of crowds, all they need to show you is the current New York Times top 10 list. That's wisdom of crowds. What matters is somebody in Amazon's vast database has bought some of the same things that you bought. And they bought a few more things that you don't have. So Amazon doesn't particularly care. It wants to sell stuff. So it says, you seem to have this soulmate whose name we can't, for legal reasons, tell you. Okay? But they have bought the following books. And, you probably want to buy them too. Collaborative filtering. You heard about this, right? You never thought about soulmates with respect to collaborative filtering. What's collaborative filtering? It's automatically finding soulmates and then seeing what they have in their closets and recommending it to you. Those are implicit links. And that link is available only to Amazon, not to you. Okay? If I depend upon my friends to buy the kind of music I like, then I'll just be listening to the music they like. Whereas Amazon probably, or any one of these big things will probably have my buying habits, and then it can compare it to somebody else's buying habits, and then sort of decide who are the people who are closest to me. Do you understand what I'm saying? So that is an interesting way in which social network analysis gets used. You don't have to think of social networks as just the human social networks. There are multiple ways the same ideas get used. Okay? So that's the other thing about social networks. The third topic that we are going to extend, for each of these slides, basically we'll spend some time in detail as to how we use these ideas in the context of web. Okay. The third topic that we're going to talk about is information integration, which is basically database style retrieval. We will actually, when we start talking about IR, which is somewhere in the middle of today's class, we'll make a connection between information retrieval and databases. They're connected but quite far apart. Here we are talking about databases. Many of you know databases. Okay, The interesting thing is, of course, what they have done is they have a cleaner model of query processing. Okay, there is data, structured data, there is a query, and you can tell, the database manager can tell whether a tuple is an answer to the query or not. It doesn't need to ask, okay, I found this answer, do you think it's right? You don't need to, no database manager ever asks you that. It knows, if you knew what your query is, and I'll assume you knew your query, you wrote it in SQL, I can tell you that these tuples directly satisfy this SQL query. Okay, and so they will essentially, given a single relational database and which has a schema and some tuples and a relational query, you are trying to return, if you are a traditional database, all tuples, all records satisfying that query. No more, no less. You don't talk about precision and recall in databases, not traditional databases. Because the reason is you're not supposed to say any more than you should say, and you're not supposed to say any less than you should say. If you do either of them, you get 0 points as a database. Traditional database. Since the requirements are so strict, you don't talk about precision and recall. You're supposed to have 100% precision, 100% recall. Now, if all databases of the world have 100% precision, 100% recall, then how do you compare them? Of course, the color of the database or how fast it is and which company sells it. Because, the correctness is required part of the database design. Do you understand what I'm saying? So that's traditional databases. So return all tuples satisfying the query. Evaluation is soundness and completeness, which is, before you even are allowed to sell the database, you should make sure that your engine is sound and complete. That means it never return a single tuple for a single query. That's wrong. Or it will never forget to return single tuple, answer tuple for a single query, which is the actual answer tuple. Right? If you do that, then you have to, apologize profusely and take that software back and redo it. Okay? So mostly we compare databases in terms of efficiency. That's your traditional view of databases. Okay? Now, but lots and lots of databases are on the web now. Okay, this traditional view almost doesn't exist anymore. Most of the databases are on the web. They're accessible to you. Okay, one of the interesting things that means is there are many databases on the web, not a single database. Each of the databases have different schemas. So a query needs to know what schema it's referring to. Each database has a different schema. So now you either have to put the user in this funny position of you need to write one query for each of the 10 million databases that are on the web, or you provide a uniform interface of some sort where you write the query with respect to a mediator schema. Mediator is a program which then mediates between you and all the databases. So rewrites your query into the schema of those databases. Do you see what I'm saying? Now, obviously, the second one is the only reasonable thing, because if you want to support the querying of all these databases in an efficient way, you need to support that. Okay? So then how do I deal with different schemas? Okay? And furthermore, all databases are, so one of the other interesting questions is, here you just assume that the database is complete. So as long as I give you all the tuples that satisfy that query in this database, and none of the tuples from this database that don't satisfy the query are returned, I'm considered sound and complete. Now you are essentially thinking of the web, there are multiple databases. Now the question is, if all of them are sound and complete, then I just need to call one of them. So suppose I'm asking, a query such as, what are all the movies made by Woody Allen? If I only have single database, I'll just give my query to that single database, take whatever the database tells me. If on the other hand, I have many databases accessible on the web, different movie sources, what do? Do I send this query parallel to all of them? Do I just call one of them? Now the reason I can't call just one of them is because I kind of know that none of the databases are necessarily complete. They may be partially complete. Okay? And a simplistic idea is to call every database for every query. That would work. But then that will increase the network traffic, it will increase the cost of query processing, and at some point of time people will also start choking your access to the databases. So the question then is, which subset of the databases are you going to access? to answer this query completely, or as completely as possible. Now I just said something heretical. I said as completely as possible. Database person never says as completely as possible. That's not part of the story. You don't have the flexibility of I'll do as good as I can. No. You have to give all the answers that are in this database. However, when you're looking at the web, there are multiple databases on the web. To some extent, you can think, actually, we'll talk about it when we get there, that you can imagine that at some long distance past, there used to be a universal shiny database that got split into pieces. Some parts got lost. Some parts are remaining under different. This is the Tower of Babel reinvented for information integration. So all of us apparently used to talk the same language sitting in Iraq long back. You understand what I'm saying, right? And then Tower of Babel happened, and then we all talk English in bad accents. Okay. So anyway, the point is that if in fact each of these are really pieces of the overall big universal database, what I really want to know is what would have been the answer if I sent my query to that universal database which doesn't exist yet. And can I get that answer from only the pieces of that database that are available? This is a very beautiful conceptual view that will actually wind up helping us later on. So you can think of each of the databases on the web as, if you know that idea of views on the databases. Any of you, have you heard the word of view of a database? Okay. So basically you can think of each database on the web as a materialized view of a virtual universal database which no longer exists. And you want to know what would have been the answer to this query from that database. You understand what I'm saying? So, Erdos, Paul Erdos. Have anybody heard of the name Paul Erdos? Who is Erdos? It's a number theorist who is very famous. We'll talk about him multiple times. He's famous for a very interesting reason. We'll talk about him in the context of social networks, because the guy used to socialize with people by writing papers with them. Okay? But Erdos also is famous for saying that if he saw a particularly good proof, he would say, that's the proof from God's book. So his God basically doesn't do wasteful things like taking care of healthcare and stuff. He writes proofs. He or she writes proofs. And he has the right proof for each theorem. Okay? As mere mortals will come up with awkward proofs. And once in a while we'll hang on to the right proof, and he will look at this. And Erdos, of course, is our mediator. He looks at our proof and says, that is for the God's proof. That's the God's proof. So it's in the God's book. So in some sense, the mediator system, the view that I'm talking about is, can I get the answer that was in the original God's database, the virtual database, which no longer exists, given that I can only access the pieces of it that are somewhere. That's what we'll spend time understanding in the information integration. Okay. Of course, there are also other problems, partially complete. These databases are also overlapping, which is why if there are two copies of the same database, calling us both of them is a waste of time. As a computer scientist, you should waste your time. There could be heterogeneous, there will be heterogeneous schemas. Each of them call the same attribute by different names. Okay. There could be access limitations. In fact, I don't know, Amazon puts its information about all the books in what you think? Database, right? So that's, and then it gives you an interface to request information about the books, right? So you can pretty much, and it'll return all the records from that database. In fact, it supports what's called a keyword style interface to a database in the background. Okay, now what are all the queries it supports? If it's a full database, then you should be able to ask it any query. I want you to do the following thing for me. Ask Amazon for all the books which have less than 675 pages and more than, less than 675 pages and more than 642 pages. That's all. It's a well-defined query. Bezos can answer this. The guy has access to the Amazon database. It's very simple query. How come you can't answer it? Because they don't allow you to ask that question. Do you understand what I'm saying? So when databases are made accessible to you, they don't give you full access. They'll give you access based on forms. And so there are queries that Jeff Bezos can answer that you're unable to answer. Now, is it really true that you can't answer this query? Has anybody figured out a way to answer this query as I'm saying this? Yes?
Spend a long time pulling down data on every single book on Amazon?
Yeah. What is a long time? I mean, essentially just hijack a whole bunch of people's computers and make them send denial of service attacks kind of things to Amazon, asking for lots and lots of books based on lots and lots of queries. And all you care about the results is, do they have number of pages between 642 and 676? If so, you keep that book, otherwise throw the book away. You see what I'm saying? That's what you can do. And so the interesting thing is that there is actually a way of answering this query. You could have given up. You know, if you are not a computer science and hacking kind of a person, you would have given up saying, oh no, this I cannot answer because Jeff Bezos said I can't answer. Come on, I mean, you know, you send a normal query, get a bunch of books. Whenever they send the books, then they'll give more books underneath. Then you call all those books, you know, all those keywords. Keep calling more and more keywords, as you said, until you get lots and lots of books. So at some point of time, you would have crawled Amazon's database this way. Then you can use it as, you know, you can use it to answer the queries that Jeff Bezos can answer. Sometimes you might actually be able to just answer it even before the entire database is crawled. Okay, so both are possible. You know, one, there are access restrictions, so you can admit defeat and move on, or you can make query processing much more complex. Instead of running one query, you are running recursive set of queries. And you're using not only your computer, but your friend's computers until the answer comes. Yes, there was a question.
I was just saying you'd be recreating your database.
What?
I was just saying you'd be recreating your database.
That's one way, yeah. But one of the interesting things is actually you can recreate the entire database for you, one way, but sometimes you may be able to just answer, all you wanted is, you know, certain type of answer, then you may not have to recreate the whole database. Especially if I don't require guarantee that I got 100% of the answers. If I don't need 100% precision and recall, then I'll spend like 5 hours and get a bunch of books which happen to have the number of, you know, pages. Okay. Anyway, then there's also this query processing over these databases will have other issues such as network unreliability. So consequently, we need to think of newer models of databases which allow these partial schemas, these you know, overlapping schemas, these heterogeneous schemas, newer notions of completeness. You can't just say 100% precision recall or nothing at all, in which case you get nothing at all. Okay? Newer approaches for query planning, the one I just told you. You would not have thought about, you know, I give you a single query, say, which is a, you know, normal SQL query. Give me all the books whose number of pages happens to be between 642 and 676. It's a perfectly well-defined query. You could have, you know, as I said, Jeff Bezos could have, you know, given it to his SQL processor and he could have just run that on his database and then given the answer. For you to run that, you need to reformulate this essentially into some sort of a recursive query, which takes much longer to execute, but will give you the answer. Okay? So that's the kind of things that we do in this part. Okay? And furthermore, by the way, I may not have mentioned it as importantly, but one other interesting thing is database view of the world is that to be able to touch a database, you should be some sort of a Microsoft certified professional who knows how to write 3-page long SQL queries. And only those are allowed to ask queries to the big databases. That was the traditional view of databases. Now, when you are being allowed access to Amazon's database, if you had a clue as to how to ask structured queries, then you would not be writing two-word keyword queries to the search engines. Or another way of putting it is, if 90% of your day you are sending 2.5 keyword queries to Google, suddenly this page says, I accept SQL queries. And here is a page you can fill. And you'll move on to the next page. You'll never use that. So the point is that the users, when you put these databases on the web, the user population becomes a lay user population. It's no longer technically, you know, certified people. And they do what they were doing all along, which is ask queries without knowing what they're asking. So the underlying data is in a database, But the user still thinks in the IR way, which is basically I have a bunch of keywords, you have to figure out what I really want and give me the answer. So now the databases have to support keyword style queries, partially specified queries. And furthermore, in a traditional style databases, all data is complete. It's clean. There are no null values. There is no inconsistencies. You assume that your data is correct. These databases, if Amazon can put its database on the web so that it can be accessible, so can I. And I can make up lots and lots of information and put it in my database so that it will give you wrong information when you ask the query. And you don't know that it's wrong information because you didn't know the answer to begin with. Do you understand what I'm saying? Okay, so once again, you need to do things like source trustworthiness, which database are more trustworthy, which are less trustworthy. And if there's incompleteness, you should be able to guess what is the missing term, for example. All those things become important in the database. Okay. The last one that I was talking about is learning patterns from the data. And we talked about why this is useful. For example, you might be able to get features of the data, for example, like the way the Pandora guys were doing. Okay? And you might be able to look for example, clusters over the pages in terms of search engines. They might be able to cluster pages. So that's sort of unsupervised learning. Again, many of the terminologies that I mentioned here, if you don't already know that subject before, it might fly off your head. That's okay, because the part that you are responsible for in this class, I will again repeat that part. So if to the extent you need to know databases in this class, I will tell you what part of databases you need to know. Okay. Anyway, so traditional classification learning, which is a supervised learning, basically starts with given a set of structured instances of a pattern, induce the description of the pattern. So I'll give you a whole bunch of examples of some concept I have in my head, and you need to figure out what it is that I'm looking for. Okay, and that turns out to be a very nice problem. That's a way you can actually look for patterns across many things. Okay, the evaluation of such ideas, the classification learning is accuracy of classification on the test data. Okay, so you have some training data on which you learn, and the test data you're testing. Now this is pretty much obviously like what you do in classes, right? I teach you supposedly during the semester and I give you a test, and then I see how you do it. Except here, the teaching as well as the testing is much more structured. Okay, the teaching would be, a classic example would be, suppose I'm interested in figuring out what credit card transaction might be a fraudulent credit card transaction, which is something that's very important. Because humongous number of people are using your credit card as you're sitting here. Okay, and the question is, how do I find out which credit card transactions are fraudulent? So, to figure out these patterns, what you can do is you might see a whole bunch of credit card transactions. For each of them, like you take a whole set of them, and for which you happen to know the labels. The label basically being, was it shown to be a fraudulent transaction or was it not shown to be a fraudulent transaction? So, for each transaction in the training data, you know whether it is fraudulent or not fraudulent. And you're trying to learn fraudulent, the class fraudulent. Okay? So then what you do is, given the positive and negative examples for this concept, fraudulent transaction, okay, and the description of credit card transactions, which might be again in terms of attributes and values. One way is, okay, like the age of the person who owns this credit card, their credit limit, their last credit card transactions location, things like this. You throw all this in your transaction, which is all available for each of these transactions. Given all this, can I find patterns? Okay, that's what credit card transactions, for example, do. Learning over that. Okay, and if I can find patterns, then basically I can use these rules to guess whether or not another transaction is a fraudulent transaction. And then if I suspect it, I'll put a block. I mean, to me it happens all the time these days. My credit card folks keep calling me. If I try to do something on the internet, if it is like buying tickets to go off to some exotic locale, they'll think maybe you shouldn't be going. Maybe you are not the kind of guy who goes these kinds of places. So they have stereotyped me. So they call me up and say, are you sure you really are the guy who's going? And and many a time, by the time I convince them that I am the guy, the sale for that exotic location is gone. So it's now the price is back to $1 million and I don't know anymore. But that's a different story. So the point being that they can use this to catch the fraudulent transactions. This is normal traditional classification. So we use this, of course, on the web. Lots and lots of things you can use it for. But the headaches that the web brings in is that, first of all, the training data is not obvious. Oftentimes, in fact, the very part of finding relevant answers to the user's query can be thought of as a learning program, as a learning problem. The last time around, people gave this kind of query. They seem to find these documents as relevant, these documents as not relevant. So then I can learn the pattern and then say the relevance for this query is this particular rule. And then I can check whether or not a document actually satisfies that. In fact, I will repeat this in a minute, but the true way of doing information retrieval, given that it's a ill-specified problem, it's under-specified problem, is to learn what the user really means when they give these keyword queries. So you start right from there. Learning is like very much a very useful thing there. But the problem, of course, is the training data is not obvious. The users never tell you that this is relevant, this is not relevant. What actually happens is they may click on something, look at it, come back and click on something else. It's an indirect way of telling you that if I came back to the results page, that wasn't the result I was looking for. If I click on something and I don't come back to this page, then I can assume that they liked the result. So that is relevant. Now it could be that I clicked on something and then the phone rang and I went away. And so the engine thinks that I found this relevant. So there's a lot of noisy examples. Even the labels are not direct and many of them are noisy. Okay? And you have to deal with that. Training data is massive, and furthermore, some of it is indirectly labeled at least, and much of it is actually unlabeled. It's not labeled at all. A classic example is spam mail. Okay? So how do I tell whether or not your mail is spam mail? If based on the mails that you have got previously, if any of them you clicked spam, 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 then those are spam mails. The ones you didn't click, I assume, are good mails. But for most mails you haven't given, there's a lot more mails available, and many of which you did not classify. Okay? And can I use this additional data that is available? So web is full of data. The one big thing is web is full of data. Corporas are much bigger. Corpora basically is just a fancy word for large body of data. Okay? Much of it, unfortunately, is not labeled. But it is data. It is real data. Can you use real data even if it's unlabeled? So there are three possibilities. I want you to learn this concept. I won't give you any training data whatsoever. One extreme. The other extreme is I will give you the training data and I would carefully label this to be positive, this to be negative example. That's another extreme. In between, I might say, look, here is the part of the training data I labeled. Here is a whole bunch of training data I haven't yet labeled. Would you like it? Do you understand what I'm saying? Would you want to take it or not? Who said no? So, think of high school math, or elementary school math, or middle school math. Okay? There are a bunch of training examples that we call homework. Several of them have answers, so they are labeled. Whole bunch of the rest don't have answers. They're unlabeled. So left to yourself, you would remove those problems from the textbook. It's waste. It's completely wasted. To the extent you think problems in the textbook which have no answers are useful for your learning, you should also believe that data, the real data, that doesn't have label is also useful. Now, what is interesting about it? I want you to think about this because we might come back to it later, but essentially, the fact is you have data, but it's unlabeled. Now, why is that different from just, so suppose in the textbook, the even numbered and odd numbered problems, so even numbered problems I think we have solutions for even and odd, I guess we have solutions for all. But suppose, most textbooks probably just give even numbered problem solutions. Okay? Then what do we do with the odd numbered problems? You could assume one of two things. One is the guy who made the problem, carefully made the problem, checked that there is a solution, just decided not to tell you the solution. The other is they just took some gobbledygook, mathematical symbols and put a, random problem, which has probably no answer. If it's late in the night and you don't want to prepare any more for the exam, you assume that's all gobbledygook. Probably they don't have any answers, let me not do that. If you have time to prepare and you want to improve your understanding of the subject, you assume that they do have solution. The answer is out there. It's just that I need to sleep later and later and later while doing these problems. Okay? Having this belief that the answer is out there is a powerful piece of information. The data on the web, the mails in your mailbox are real mails. They're real mails. Somebody actually generated them or typed them. You may not have yet classified them as spam or non-spam. They are not randomly generated mails. Do you understand what I'm saying? A randomly generated mail means generate your email address in the from and then put random number of words from the English language into the body. A random number of letters from the English language into the body and send it to you. If I give you that data, it's useless. But if these are real problems, real mails, just like the math, even odd numbered problems were real problems, I just withheld the answer. Then it's a very useful additional piece of information that can be used in learning. And so in fact, one of the things that you would see is, so consequently, so training instances are noisy and incomplete, and much of the instances are unlabeled. So you might be interested, for example, in how can I exploit massive data, only part of which is labeled? How do I use this unlabeled data? Okay? And we will talk about techniques for that, which will almost have some sort of a circular feeling to it. What they'll do essentially is they will learn on the ones which have labeled, then apply that learned information to the unlabeled data to come up with the labels for them. Now you have fully labeled data, you relearn on this entire fully labeled data. This looks like totally circular reasoning. It works. And it works because the mails that you have or the problems that are in the textbook are not random. They are real problems. Just we did not give solutions to them. I want to make a very, very, very telling story about this, again, across disciplines. Does anybody know George Danzig? George Danzig. Okay, so this department's name is what? What? cse. It's Decision Systems Engineering, Computer Science and Decision Systems Engineering. And Decision Systems Engineering is operations research, and operations research is a huge part of it is linear programming, and linear programming has this great idea called simplex algorithm. Have any of you heard this? Yeah. Danzig is the guy who invented simplex algorithm. Okay? Simplex is this algorithm for solving linear programming, which is exponential in the worst case, and yet in practice it actually is faster than the most polynomial in the worst case algorithms. Okay? He's a very smart guy. The story about him is the following. At one time, he was a grad student at University of Berkeley, University of California, Berkeley, and in math department. And one day, being a grad student, he must have worked hard or went to a bar or something and slept late and came to the class in the middle of the class. Okay, and found that basically he had to figure out what's going on in the class, and he did see that there were a bunch of problems on the board, so he took them down. And then after the class he went back and he basically tried to solve them, and then the assumption is, of course, if you come late to the class, those are the homework problems, so he just took them down. And he had trouble solving them, so he took actually extra days, and then one day, like 3 days later or something, or maybe a week later, he went to the professor's room and said, I have the solutions for the homework. And he said, yeah, leave it here, we don't really care about your homework solutions, especially for the graduate students. You leave it here. So he left it here and he went out. And a couple of days later, late in the night, this professor is banging on his door. waking him up. Why? Why?
They were home.
They're not homeworks. They were open problems. They were open problems. So he was just saying, it's a graduate class, right? So he wrote down, here are some of the open problems in this area. Right? Okay? And then, unfortunately, he knew everything everybody knew, but for the label. For the rest of the people in the class thought they are labeled open. And so we should give up. Life is too short to actually work on open problems. Poor guy Danzig wasn't told they're open, so he assumed it's homework problems, and so he actually solved it. And so the professor was banging on his door because he wants to desperately write multiple papers and become a co-author. Which is right? So you can think about this. The point is he assumed the solution must be out there for these problems. Because they're homework problems. So because professor must have already figured out how to solve it. So I'm darned if I'm going to admit that I'm somehow less smarter than the professor. If I say open, that means, my God, nobody in the world has done it yet. And then you feel like giving up. Okay? And so, it's like, there's an interesting connection. Obviously, it's a good story to remember, but you remember this story, and then you remember, hopefully, the power of unlabeled real data. Okay, I also have opposite examples. When one of my previous batch, when I was a grad student, we had this great professor who actually did work in pattern recognition, and he's, one time in the middle of the qualifier examination, with the qualifier examination, like 4 questions of 3 hours duration. And in the middle of the qualifier examination, he comes and says, oh, by the way, that question 2 has no answer, so don't waste your time on it. So those of you who wasted the first 2 hours of the exam trying to solve that question, unfortunately, you're just out of 2 hours. Okay? So we assume that, when given a solution, when given a problem, that somebody knows the answer. And that does help, because you come up with a problem which does have an answer, but I won't tell you what the answer is. It's not trivial. You don't know this. I know this because the hardest part of teaching a class is setting exams. Okay? And so when you have a whole bunch of mails, like spam mails, that are not randomly generated, they're actual mails. You just don't know the label for it, that's all. Somebody knows the label. The truth is out there, so why can't you guess it and then use it in the circular reasoning? That's what, would be useful in this learning problem. Okay, so that's one of the things that we will learn doing when we talk about learning. And in each of these cases, we talk a little about the traditional techniques and little about how this gets extended to something in there. That's what we'll do in this class. Okay, any questions? Okay. Okay. So what I want to do next is, in the next 10-15 minutes hopefully, is talk about some big ideas, cross-cutting ideas that cut through all 4 of these. And then introduction is over. Okay? And then we will talk about IR, but IR has been talked about. In fact, I would probably say precision and recall I already told you, which is like the first one. But anyway, so a few things that I think are cross-cutting ideas, and my hope is that you would add to this corpus of cross-cutting ideas, patterns that we see in this course, are what seems to be working on the web. Okay, and I'll show you my examples. You can come up with better ones. You can use the blog to suggest ones. You can hopefully by the end of the course come up with more interesting trends and cross-cutting ideas. Okay, so the first idea is what I call, I'm being very modest and calling it big idea 1. Big idea 1 is finding sweet spots in computer-mediated cooperative work. That's a huge big idea. I mentioned this in the first day's class when somebody was saying, we need natural language processing for sure. Maybe not. You have a human in the loop who is going to look at the results. So the name of the game is not to completely bore them to death or frustrate them to death. As long as you sort of do part of the problem and they do part of the problem and they are not unhappy, you, the search engine, has solved the problem. You've done good day's work. You can go. Do you understand what I'm saying? Okay? So it's normally if I give a problem such as IR where here is the query, find the relevant documents, and there is nobody, you must be giving the relevant documents and we will judge you based on that. That's one kind of problem. The other is I give the relevant documents, the first top 10 results, and then the user sort of will be able to look at them and decide which of them they like. Do you see what I'm saying? So the users can tell which is relevant and which is not relevant. And so you are working together. It's a human-computer interaction that's going on there. It's a computer-supported cooperative work. Much of what we do on the web is computer-supported cooperative work. And you have to understand that and you have to use the human to your advantage. And I know that you are also human, but when you're writing the search engine, you're trying to use the humans to your advantage. Don't overdo the problem. Okay? So what is interesting is, so it's possible to get by with techniques that are blithely ignorant of the semantics when you have humans in the loop. The interesting part about information retrieval is an idea that we'll call bag of words model that we will talk about, vector space, similarity, etc. The interesting part about them is not why don't they work well, but that why do they work at all? How can you take a page of text and make it into a bag of words and compare that back to some other bag and assume that that somehow tells us the similarity between two documents? It should. I should be able to generate like a counterexample a picosecond for your hypothesis that this actually captures any kind of semantics. But if I am busy generating the counterexamples, you are busy making money. Because you generated a search engine which just does exactly that and people are using it and you're also showing them crazy advertisements, they're clicking on them, you're becoming rich. So what did I miss? I basically missed this point that you don't need full semantics. Sometimes you don't have it, and more importantly, you don't necessarily need it. You don't need to solve natural language processing problem to be able to make headway in computer-supported cooperative work, which is what we are doing. But then there are sweet spots. Not every idea works. Okay, full NLP is too costly. Bag of words works. Why don't we try bag of letters? English is one of these great languages where there are only 26 letters. As long as you're taking a big file and converting into a bag of words and saying it has 5 instances of the word love, 9 instances of the word university, why not just say it has 3,000 instances of the letter R and 4,500 instances of the letter U? And then compare two documents in terms of bag of letters similarity. It turns out that the techniques that we use for comparing two bags will work, whether the bags are made up of letters, are bananas, are pineapples, are words. It will work. But basically, it's not going to be making the guy, the human in the loop, any happy. So why is it that the sweet spot is at bag of words, not at bag of letters? And in fact, as you go from bag of letters, here is bag of words, this bag of letters, and then further down, so if this is words, letters is even cheaper to do, but probably useless. And then I can talk about bag of sentences. Instead of words, I can talk about bigrams, that means two words together. K-grams, K words, K consecutive words together. Eventually sentences. And then I compare two bags in terms of the sentences that they have. That would turns out to be much more useful in terms of having a much higher level of precision. So in fact, you can think of these three ideas in terms of the ideas of precision and recall. Bag of letters has a very, very high recall, but pretty low precision. Bag of sentences has very, very high precision, extremely low recall. Okay? And in between, bag of words has just about the right level of precision and recall, the Goldilocks sweet spot. And so then you can use that to make the user in the loop help you out the rest. Can I tell you where the sweet spots are for everything? No. That's why I put this in the beginning of the course, rather than give homeworks on this. Your homework is come up with more sorts of things like this, so that we can all see the patterns. I think this is an important thing, figuring out the sweet spot for each of these problems. Okay? Yes. It came one slide today. So imagine that I showed this first and I showed the other side. Okay. The second idea is collaborative computing or brain cycle stealing or computizing eyeballs. Okay. Again, it comes from the same idea that you are now talking about humans and machines doing work cooperatively. In fact, web has access to not just a whole bunch of pages, but a whole bunch of people staring at pages. The question is, and in fact, it's very well known that the most underused CPU in the universe is the human brain. Okay, well, actually, not really well known. Some people say that we are doing some stuff all the time. We are checking at least our email, all the time. But generally, we have a lot more CPU cycles than we seem to be using. Right? Why can't we make use of those CPU cycles? Okay, I'm talking about we are our own enemies. When I say we, that means all of us have idle cycles. But now I, the smart search engine maker, who is just one of us, will use this against you guys to make myself a lot of money. Okay, so the question is, how can I use all these idle human beings to solve problems for me, which normally cannot be solved until everything is automated. When AI becomes complete reality, everything is automated, then you don't need to solve these problems by humans. Humans don't have any work. It'll be one of those cartoon movies where we will be basically used to generate, I guess, battery energy or something, and somebody else will be having fun. But until then, the question is, can I make